All right, so this is day 2 of what if a line does not fit the data. And what we're going to find out today is that sometimes you get what's called a piecewise model. According to your exponential model from the previous problem, we found that we could use y equals 175.17 times 1.066 to the x. How much oil was produced in 1996? Remember, year 0 was 1900. So if we take the equation 175.17 times 1.066 and raise it to the 96th power, because 1996 would be 96 years since 1900. Clearly, we would want to leave the number on the calculator screen for 1.066 to the 96th power. It's approximately 462.053. And we would get y is approximately 80,937.79716 and so on. So what we're really saying is we are predicting in 1996 about 80,938, and that was millions of barrels. Below is a continuation of the data for the amount of oil production. So what they did was they gave us a table of data for years later than what were in the original. And what you'll notice when you graph them, you get this kind of funky little quartet of points. And then you get sort of another little section that looks like it's got a pattern, but it doesn't seem to follow the original pattern. It says below is a continuation. Compare your prediction for 1996 to the amount given in the table. Why was your prediction so far off? So the 96 prediction was only 23,360, and we were predicting something over 80,000. So what we would find, we could say, is that the exponential model was much higher than the actual. And then there's a phrase that comes up. It says it's too far removed to be extrapolated. Too far removed to be extrapolated. And what that means is that after a period of time, a pattern that might have worked for a while doesn't always continue to work. And what we can see from the graph is that if we continued this exponential model, it doesn't hit any of these points over here on the right at all. So what we're going to look at is a piecewise graph where maybe it follows a pattern for a certain period of time, but then it might change the pattern that it's following. Add the above data to the previous data already in your calculator, create an updated scatter plot on your calculator, and sketch it. So this one would be an updated scatter plot of the original set of data plus the additional points in the top right. Does your exponential model continue to fit? And we would say no. Does not work well past 1972. Which is probably why this set of data was chosen. Plot just the data from 1982 to 1996. So if we plotted just the points in the table from 82 to 96, and we're going to treat 82 like year 0, like our new year 0, what model do you believe will best fit this data? So if we're just looking at these points, they look pretty linear. And so if we zoom in, so to speak, on just that section, it really does look pretty linear. It doesn't look terribly curved. So we're going to guess linear. Use your calculator to determine a regression line, least square regression line from the data from 1982 to 1996. So I've already cleared my memory. I've turned diagnostics on. I then went into stat edit and I entered the data from 1982 to 1986. Notice that year 0, 1982, and then it goes up as far as year 14, which is 14 years later, 1996. If I go into where the y equals should be, you'll notice nothing is there yet. I can go up to plot 1 and make sure that it's turned on, or I can do second y equals and select plot 1, make sure that it's turned on, that it's on the scatter plot, list 1 and list 2. Remember, when you hit graph, you are probably not going to get this. You are probably going to have to press zoom and go down to zoom stat so that it will zoom in on just the data you want, and it matches my sketch over here on the right. Now, in order to get that least square regression line, second stat, Oh no, what's going on here? I don't have that residuals. Let's see. Second quit. Why don't I have residuals? Because I have not calculated my least square regression line yet. Option 8. So least square regression line, option 8. I want list 1 and list 2. I want to click vars, y vars, number 1 because it's a function, and number 1 because I want to save it in the y1 spot. And now I can calculate. Now I've got my data for my least square regression line. If I press y equals, you can see that it is stored it there. And if I now press graph, I can see that it fills in my least square regression line on the actual scatter plot. So if I go back, my least square regression line was y equals 292.7 for the slope, x minus 4,695.1 for the y-intercept. It says comment on the residual plot. So this is our scatter plot. It appears to be linear, but we want to check and see if the residual plot also lends us to believe the same thing. So I would go second stat. You can see residual is now there, so that's good. Stat, edit, and in list 3, and I go all the way up to list 3 because I want to fill in the whole list. Second stat, and I'm going to fill that list in with the residuals and hit enter. So now I've got all my residuals for all of the individual points, how far above or below the fitted line they are. Second stat plot, it is on, but I need to change it from list 1, list 2 to list 1, list 3. And when I go to graph it again, all of the points are gone. That least square regression line is still there. So I can hit y equals, and I can turn that line off by highlighting the equal sign and hitting enter. And you can see now there's no solid bar anymore on it. So it's going to be turned off. If I press graph, now the fitted line is gone as well as my coordinates. Zoom, and I'm going to go down to zoom stat, which was option 9. And now you can see the residual plot it looks curved to begin with, but don't forget that there is a point right here. So I do have 4 points above, 4 points below, and they are sort of scattered from left to right. And the big deal here is this one on the left. It does not look like there is a solid pattern. You might try a fitted curve and see if it's any better. But this one had a pretty decent set of data for our R values and R square values, both being like 0.99 and 0.98. So it's pretty solid. But you could, if you wanted to, they asked us specifically to do a regression line, but it does not appear, no apparent pattern. So linear model is a good fit. If you wanted to, just for the sake of argument, you could go in here and go stat calc and go down to option 0 and see if we felt like that was any better. 0.98, 0.99. So it's got similar R and R squared values. I'd have to turn my stat plot back on to list 1 and list 2 and graph it. And wait until that little thing in the top right corner stops moving, because right now it's thinking. And I would go zoom stat. And not a significant difference. It doesn't look like they're any significantly further away or closer. The real information to be gathered on this one would be that I would have to go back into my table, delete all of those residuals, and then go up and ask it to do it again now that I've rerun for an exponential regression, and see if I do the stat plot this time. When I switch it to list 3, do I get a residual plot? Again, it's thinking while it's graphing, so it won't let me switch screens. So this time I am going to turn that on and turn that line off, and then zoom stat. And that doesn't look any significantly different. So it looks like actually a linear model or an exponential model could be used, and that the data is not going to be represented significantly different. Interesting. All right. I'd never run that before as an exponential because it doesn't ask for it, but it doesn't look like an exponential model would be bad either. With this new linear model, can you make a better prediction than you did for the amount of oil produced in 1996? So if when we tried to use that original curve, we were, I don't know, 55,000 million barrels off. So this time, if we do 292.7x minus 4,695.1, and we plug in 96 because we are 96 years since 1900, we would get, let's see, 280992. Notice that I am using something that looks like slope-intercept form. We are going to say a prediction of 23,404.10. That's my result of the subtraction down here. That's my prediction using the equation. If we look back at the table, the actual was 23,360. So very, very close. That's nice. That's a very small residual. So this clearly was a better prediction than the original curve from the day one data from 8.2.2. Since you use two different models for the data, you'll need to make a piecewise graph that shows both models. On the scatter plot of the oil production data with the piecewise model, add both the exponential best fit model and the linear best fit model. What is the domain of each? So if we had y equals 175.17 times 1.066 to the 96, this one is, and I won't put 96 there, I'm going to put x there. This was the original graph, and we said that the domain was from 1905 up to and including about 1980. And so our x values would be 5 to 80. And the second one, you even could cut this off at 72 maybe, depending on whether or not you wanted to skip the 74 to 1980, that little quartet of points altogether. You might be able to just skip that. Y equals 292.7x minus 4,695.1. The domain for this would be from 1982 through and including 1996. So we would say x values of 82 to 96. And you would have a little gap in the middle where there wasn't a good representation for a very small amount of time. Neither one of these models worked really well. Remember in problem 881 where Mitchell wondered if he could write the equation of an exponential function that passed through the points, and he solved y equals ab to the x equations, and he determined that a was 64 and b was 1.5. He had another idea. He wondered if he could use the regression functions on his graphing calculator to determine the equation. So if we had an x value and a y value, we had 2, 144, and we had 6, 729. And we did, let's see. I didn't have my calculator set up for this one. So I'm going to reset the memory. And I'm going to turn diagnostics on. Have to do that every time. And let me do a table. No, I'm going to go to stat, and I'm going to enter the 2 points, 2 and 6 and 144 and 729. And I'm going to see if it'll do it for me just with those 2 points. So I'm going to stat calc, and I'm going to go down to 0. And I'm going to ask it to store it again in yvar's function y1 and calculate it. And there we go. It gave us the 64 for our A value and our 1.5 for the B value. So if we use the exponential regression and we use list 1, list 2, and we save it as a function in y1, and we did this in table, which was the edit function, we got that A equaled 64, we got that B equaled 1.5, and it will still give us the same equation that we got from doing all of the calculations on 8-106. Now, from the previous question, 8-81. I am going to tell you, this is going to be your backup. You're going to need to still solve algebraically for questions like Mitchell's with the exponents, with the equal values method. But this is your backup method, right, to double check your answer. Does Mitchell's method work for determining linear equations too? Using algebra, write the equation of the line through the points and then use the linear regression function on your calculator to test. So if we were going to test this one out and we were just going to do a linear equation. So this time we were going to assume that the 2 points are in a line and not in a curve. So we would say we could do 729 take away 144 over 6 take away 2. We'd get 585 over 4, and we would get a slope of 146.25. We could do 144 equals that slope times the x value 2 and solve for our b value. This is, going way back to even 8th grade where we were solving for the slope and the y-intercept, and we would get negative 148.5 equals b. So we could write our equation y equals, the slope is 146.25, x minus 148.5. Now the question being presented, if we used the same data, the same 2 points in our graphing calculator, and we asked it to stat calc, and we went to linear regression, and we're going to save it in the same place as a function in y1, is it going to give us a slope of 146.25, and it's going to give us an intercept of negative 148.5. And you will notice that your r squared and r values are both 1 because you're just finding a straight line between 2 points. So guaranteed you're going through both of them perfectly. But your graphing calculator is backing up the same data. If we do linear regression and we do list 1, list 2, and save it as a function in y1, we get that A was negative 148.5. We got that B was 146.25, and it supported the answer that we got manually. So super interesting that we can now use our graphing calculator to check our work, even for creating an equation, whether it's exponential or linear, from a pair of coordinates.